In this lecture, we will start our discussion on inviscid and viscous flows. Let us look at the concepts. We will first look at the basics of both inviscid and viscous flows. We will discuss about flow friction caused due to viscosity, slip and no slip conditions, attached and separated flows, the role of adverse pressure gradient, and the concept of substantial derivative and its role in fluid element acceleration. Let us look at the basic concepts of inviscid and viscous flows. So, to begin with, we recall about the random motion of gas molecules which help to transport mass, momentum and energy through the fluid medium from one location to another. And the transport on a molecular scale gives rise to some of the macroscopic phenomena that we are aware of. A, mass diffusion. So, that occurs when you have gradients in chemical species. So, if there are variations in the concentration of different chemical species, there would be mass diffusion, and an example of this would be chemically reacting flow in a combustion chamber of a gas turbine engine, for example. B, friction due to molecular viscosity, and this happens when you have gradients in the velocities in different parts of a flow. So, that would lead to frictional effects in the fluid field. C, thermal conduction, which occurs due to temperature gradient existing in the flow. Now, in all gaseous flows observed in nature, you would be able to see these transport phenomena in action. Such flows are called as viscous flows, and they manifest these effects, which we call as viscous effects. Not all of them may be simultaneously present, but some of these effects would be present in all viscous flows. Some aerodynamic flows are dominated by viscous effects, and that is of interest to us. So, if an airfoil is pitched up at a fairly large angle of attack, then the thin layer which is affected by viscous effects around the airfoil has a tendency to move away from the surface and separate from the surface of the airfoil, especially on the top surface, which we call as the leeward surface. Once the flow separates and leaves the surface, a large wake is formed behind it, and because of the wake formation downstream of the body, we find there is a dramatic increase in drag and reduction in the lift of the body. This reduces its aerodynamic efficiency. We call this as a stalled airfoil. Separated flows are also observed in blunt or bluff body geometries, not only on streamlined geometries at large angle of attack, but also on bluff or blunt geometries like flow past a cylinder or sphere, and in that case the flow expands around the front face of the body where it remains attached, but then it separates from the surface on the rear side of the body, and that forms a wide wake downstream of the body. Now, when air flows over a solid surface, friction exists between the surface and the air. In fact, friction exists also between different layers of air. Consequently, it retards the relative motion between the air and the solid surface. This has an effect on both the solid surface and air in the form of an action reaction pair. The surface feels a dragging force in the direction of the airflow, which acts tangential to the surface. And we recall that this tangential force per unit area is defined as shear stress, which we designate by tau And you may also recall that there are different components of this shear stress like tau x y, tau y z, tau z x and so on. So, an equal and opposite reaction is felt by the air which is adjacent to the surface, and thereby its flow velocity decreases. The maximum influence of the friction exists at the surface. This is a very important point. The effect is not equally felt everywhere, it is maximum at the surface. Thus, the relative velocity between the surface and the air becomes 0 at the body surface for continuum flows. When the air becomes rarefied, that means its density becomes significantly low, like for example, at higher altitudes within our atmosphere, then there could be some slippage at the wall. But for continuum flows, it is a 0 velocity at the body surface. This is called as the no slip condition, and this is a distinguishing feature of viscous flows. Now, when you observe the air by gradually moving away from the surface along the surface normal direction, the flow velocity gradually increases. This variation is represented through a velocity profile. The region of flow near the surface has large velocity gradients which are produced due to the frictional force between the surface and air. So, if this is your surface geometry, if we draw normal vectors at different points on the surface and we have some means by which you can measure the velocity or we can calculate the velocity varies like this as it moves away from the wall. So, what you are seeing is that near to the wall, if you zoom very closely on this part, there are rapid changes in the velocity as you move in the wall normal direction. So, if you call this profile V, which is basically a function of n, then dV dN is large close to the wall, and then as you move away from the wall, the dV dm gradually becomes very small and limits to 0. If it is a very thin region over which this change is taking place, we often call this as a boundary layer. This thin region would then be represented by delta, and then we say that this delta is much smaller than the characteristic dimension of the body geometry. So, this C, for example, could be the chord of an airfoil, and delta could be the boundary layer thickness formed on the surface of the airfoil by virtue of the velocity distribution. That was a little bit on viscous flows. Now, let us have a look at inviscid flows and let us look at the important points. So, if there is a flow where there is no friction, no thermal conduction or diffusion, we would call it an inviscid flow. So, an inviscid flow will typically slip over the surface because of absence of frictional effects between the air and the surface, and it can only have a tangential velocity component at the wall, but no normal component should be existing there. Okay. So, only tangential component exists. Now, inviscid flows do not truly exist in nature, they are basically hypothetical. However, there are many practical aerodynamic flows where their influence is very small, and we can model the flow as though it is close to inviscid. Theoretically, inviscid flow is approached in the limit as Reynolds number goes to infinity. We will discuss more about Reynolds number. It is one of the very important non-dimensional numbers which is of enormous importance in aerodynamics. For practical problems, many flows with high but finite Reynolds numbers also show nearly inviscid behavior, and therefore, the effect of friction or thermal conduction or mass diffusion, it is limited to a very thin region adjacent to the body surface, which is the boundary layer. We were just discussing about the boundary layer few minutes back. So, beyond the boundary layer, that is beyond this thin region the flow is essentially inviscid. That means, once you have crossed the boundary layer, the extent of the boundary layer, beyond that the flow that lies is practically devoid of viscous effects. Inviscid theory is very powerful in predicting pressure distribution and therefore lift on the body when the angle of attack is not substantially large. The results are very encouraging, and it can also predict the flow field patterns through the streamlines well. It is especially true for streamlined bodies or slender bodies like airfoils, especially at low and moderate angles of attack. However, as we have seen that at high angles of attack the flow can separate and viscous effects can then dominate the flow. In such a case, it becomes very difficult for inviscid theories to predict the pressure distribution well. Neither can it predict the aerodynamic drag, because the inviscid theory cannot account for the drag effects. Here is a diagrammatic representation of an airfoil facing a uniform flow. So, there is a uniform flow field which is approaching the airfoil from upstream. So, what we mean by uniform flow is that at every spatial location that you have, you see the same value of the velocity magnitude. So, that kind of a flow is approaching the airfoil. As it nears the airfoil, of course, it moves around the airfoil and the streamlines get bent, as you can make out. Now, we are looking at the flow past the airfoil at two different angles of attack. One is a low angle of attack, where you have the flow nicely remaining attached around the airfoil as it moves, and as it moves you are seeing that there are a few dotted lines. One dotted line which is within the airfoil is the airfoil cord, which connects its leading edge with the trailing edge. The remaining dotted curves, they are representing the extent of the boundary layer and the region which is having viscous effects. It includes the thin wake which moves downstream of the airfoil. So, this is the region within which all the viscous effects are confined. Flow outside the boundary layer is practically inviscid. So, this is typically the situation at a low angle of attack. So, this is small alpha. Then if you look at another situation where it is a large angle of attack and we have chosen an angle which is typically beyond the stall angle of the aircraft, then you find that the flow has separated. How can you make out that the flow is separated? The flow is very, very different from what you saw over here. It is no longer enveloping the body nicely. It follows the body surface up to some distance and it seems to be leaving the surface beyond that. Of course, that does not mean that it ends up creating a vacuum in the separated region. Only thing that it means is that the streamlines cannot remain attached and cannot follow the surface entirely, and the problem is felt on the leeward surface or the upper surface of the airfoil. So, you can see a so called flow separation point from where a streamline seems to be leaving the surface. It is no longer following the surface of the airfoil. So, we would call that streamline as a separation streamline, and what is left behind that streamline and the leeward surface of the body is a wide wake which is formed behind the airfoil, which contains reversed flow region. So, usually the velocity within this region which will be much smaller than what you see in this region, which is practically inviscid beyond the separation streamline, and the wake is a very much viscous dominated region. However, the flow remains nicely attached on the lower surface of the airfoil. Now, if you look closer at what is happening at different points on the airfoil, we have chosen 2 points 1 and 2. The point number 1 is a point close to the leading edge of the airfoil and on the upper surface, and the point number 2 is exactly at the point from where the separation streamline is leaving the surface. We often call that as the incipient separation. That means the flow is on the verge of separation. So, at point number 1 where the flow is well behaved, it is attached. You see a typical boundary layer kind of velocity profile developing in the flow field, and we have marked the S coordinate which is following the upper surface. Here the shear stress, if you calculate it, would be greater than 0. Typically, this shear stress which we learned in our earlier lecture, if it is in the xy plane, we will be typically interested to look at one of the components of shear stress, that is tau xy, and only that component will be non-negative. And then if you recall the expression of tau xy, it is equal to del v del x plus del u del y. Now, if you imagine that the surface is flat locally and you can orient the x y axis like this, then you can still simplify this tau expression and express it as u del y, because the del v del x will vanish in that case, and this will give you the shear stress on the wall. That means, the del u del y of that velocity profile that you work out exactly at y equal to 0 will give you the wall shear stress. So, you can see very easily that it is dependent on the velocity gradients. Now, if you have a velocity profile looking like this, as you move along the y direction, for a positive change in y, the u also changes by a positive amount. So, it is like delta u by delta y, where y tends to 0 and both of them are positive, and therefore, the shear stress will be positive. So, in a location like this, shear stress is positive, but where you reach a point where the streamline is about to separate from the body surface, the velocity profile looks very different. It looks like the one we have drawn over here. So, from the profile you can make out that if you were to calculate the del v del n along the wall normal direction, then that is equal to 0 over here. The velocity at the wall is 0 because of the no slip condition, and as you move along the n direction, for some distance the velocity remains 0, then it gradually picks up. What that means is that the normal gradient of the velocity is 0 at the wall, and the shear stress, which can be worked out like this, mu del v del n, therefore, the tau will go to 0. So, the velocity profile at flow separation point is given by this, and it inevitably means that shear stress has gone to 0 there. So, it was positive at a point like 1, it becomes 0 at a point like 2. If you go beyond and you try to see what happens at a point 3, which is well into the separated region, you will find that at point 3 the shear stress goes below 0. Let us look at some more details, and here we are going to focus on the role of adverse pressure gradient. So, let us see what that means. In a geometry of the body which looks like this, the flow will gradually decelerate by virtue of the geometry. This is typically what happens on the upper surface of the airfoil beyond stall angle, and it is found that the pressure also gradually increases as you move downstream following the surface. We have marked 3 different points which are located on the surface, and at the 3 different points the pressure is growing gradually. When pressure increases as you move along the body, then we have a situation of adverse pressure gradient, dPds greater than 0. You remember that we talked about gradient of P, and then we talked about dotting it with ds, and we said that that gives you a directional derivative, and if the directional derivative is dPds here, then the directional derivative happens to be greater than 0. So, if you move along the s direction, the pressure is increasing. That is a situation of adverse pressure gradient. That means a pressure gradient which is adverse for the flow to remain attached, and therefore, it becomes more susceptible to separation, and once it separates, you have a reversed flow region. What do we exactly mean by a reverse flow region? You find locally at this point 3, for example, some part of the velocity is pointing in the opposite direction to the flow direction. So, the overall flow direction is this, but in some region of the velocity profile, locally the velocity is pointing the other way. So, that is a reverse direction, and therefore, we say it is a reverse flow region. The dotted region is all going to be affected by reverse flow and viscous effects. On the lower side of the airfoil, on the contrary, the flow is facing a favorable pressure gradient. By virtue of the geometry there, the flow encounters a situation where pressure is continuously decreasing as the flow moves down along the body surface. So, we have marked 3 points here, and you find that dPds is less than 0. The flow therefore remains attached, and this is typically a situation where the pressure gradient is favoring the flow to remain attached to the surface. Now, if the pressure gradient was 0, you would have a neutral situation, whether it neither assists or it does not make it adverse. That means, pressure remains constant. In that case, the velocity is neither accelerated or decelerated. It remains constant as you move from one point to the other, typically a flow over a flat plate if it has reached a fully developed condition. So, that is how you would see the effect of adverse pressure gradient on a streamlined body. If it was a blunt or a bluff geometry, you would usually see a much wider wake behind the body, like what we have seen here, and usually an upper separation point and a lower separation point due to the large width of the body. And as you may recall, the same kind of phenomenon is occurring over here, where the flow gets detached. So, let us expand on these thoughts a little bit more. Now, we would develop a small tool before we move on, which we call as substantial derivative. It is important for us to understand how a fluid element will be affected as it moves through a flow field developing on a body. So, like we said that you are following the body and you are identifying different points at which you are looking at the pressure, looking at the state of the boundary layer, etc. We are interested to look at a small fluid element and whether it accelerates or decelerates, what are the forces that it feels as it moves from one point to the other in the flow field near to the body surface. for assessing that, we need a very important tool which is called as the substantial derivative, which will help us to quantify the acceleration of that fluid particle under the influences of the different forces, primarily the pressure gradient and the viscous forces. So, let us see what this substantial derivative is all about. So, let us say we are looking at the density of the flow field and we are looking at it as a function of x, y, z and t. We are looking at 2 points 1 and 2 and they are not far apart, they are close to each other. In that case, we can think of expanding this function rho about the point 1 in a Taylor series. So, we expand it in a Taylor series and you will be able to write it in this manner by including the different partial derivatives of rho with respect to x, y and z as well as the time. So, you are going to write it in this manner and then all these derivatives are being worked out about the point 1. You will be having higher order terms over here, including say second order derivatives like this in space and time and so on, which are neglected. These are the higher order derivatives. Okay. Now, if you divide this expression, both sides of it, by taking the rho 1 to the other side and then taking dividing it all through by T 2 minus T 1, what will you be left with? You will be left with del rho del x 1 and then you will be left with x 2 minus x 1 by T 2 minus T 1 . And in the last term you will be just left with del rho del t. Now, if you say that T 2 tends to T 1, that means essentially T 2 minus T 1 tends to 0, then in that limit the rho 2 minus rho 1 by T 2 minus T 1 will be called as capital D rho dt, which is the substantial derivative. In the limit that we have applied, where the time T 2 approaches T 1, we will find that these terms will also turn into derivatives. This will become dx dt, this will become dy dt, dz dt, and therefore, that is nothing but the u, v and w components of velocity of the flow field. Therefore, what do we have finally? We have d capital D rho dt is equal to u d rho dx plus v d rho dy plus w d rho dz plus d rho dt. So, this is the local derivative, as we say, which means it is the change in density at that location, that is 1, because of the fluctuations in the flow field. We have talked about transient variations in the flow properties at a specific point in the flow. So, that gives you the local derivative, while the rest of the terms is dependent on the movement of the fluid element through the flow field, and therefore, that is not a local effect. Because these terms are related to the convection or advection of the fluid element through the flow field, these terms are called as convective derivatives. So, finally, what do we have? The substantial derivative can be expressed as an operator and we will introduce the del operator once again over here, because that will give us some convenience. In terms of the del operator, you can understand that the substantial derivative can be further expressed as V dot del, because V is U I plus V j plus W k, and we have already written the del operator. So, when you dot these two, it produces U del x plus V del y plus W del z. So, we have been able to work out the expression of a substantial derivative. We will conclude this lecture by saying that we discussed about some basic concepts of inviscid and viscous flows in this lecture. We discussed about slip and no slip condition at the surface over which the flow takes place. We discussed about adverse pressure gradient and its influence on flow separation in viscous flows, and we are going to expand these concepts further in the next lecture. Especially, we will start off by applying the substantial derivative on the different conservation equations. Thank you.